Good afternoon. Thanks for coming to our senior design presentation on design analysis and multi-objective optimization on Winglets. My name is Abraham Neese, and I'm part of the Thomas already. Lift forces are created by the greater pressure forces on the lower surface of the wing and the lower pressure on the upper surface of the wing. These forces tend to equalize on the wing tips, creating vortices. These vortices create additional induced drag on the aircraft. The more induced drag on the aircraft, you have more fuel consumption. Therefore, it's important to address this issue. One way of addressing this issue would be with winglets. The benefits of winglets are, overall, you have lower fuel use and more fuel efficiency. Another added benefit would be that your aircraft trailing in the wake of this aircraft experience less turbulence in that region since there's less vortice effect. Another benefit would be that since the engines are operated at lower settings, you have less fuel emissions, carbon emissions, you have less noise pollution, and another benefit would be to achieve takeoff velocity. You can do that in a short amount of time. And now we'll talk about Japan now.
All right, so how did we go about generating our geometry for our design? For our simulation, we made this model in SolidWorks, and this is a 3D rendering view here. And we wrote a Fortran code to optimize the geometry based on 9 parameters that we will input into ANSYS for our simulation.
Okay, so the approach, as we know, we are controlling our geometry with 9 parameters. One parameter that's set is the airfoil of the winglet itself. Now this airfoil, the PSU 90-125, was actually invented by Mark Malmer at Pennsylvania State University. This airfoil features very little laminar separation at high Reynolds number, as you can see in the X-Pol analysis. And it also it keeps the flow subsonic all throughout the airfoil, which induces shock-induced drag. So it's very, very positive benefit for us. And now the analysis by Sinead.
So for the analysis, we had to mesh our geometry since we're dealing with Navier-Stokes equation. So we use 3D computational bridge generation and we did surface meshing because we're dealing with the surface of the wing and not so much the internal structure. And we did refinement near the surface of the winglet for more accurate results. And effective meshing, it leads to increased results, accurate results, and it's also low computational cost.
Okay, now computational fluid dynamics, CFD for short. We'll be using ANSYS Fluent. ANSYS is a finite volume solver which actually has three equations integrated: the continuity equation, the Navier-Stokes momentum equation, and the energy equation. We'll be using a density-based solver because we are operating at a very high Mach number of 0.8, so we are expecting shock waves, actually compressible flows. So a density-based iteration scheme actually takes this into account. Our turbulence model will be the shear stress transport. First of all, it is very important to model the boundary layer phenomena, which is taken into account by shear stress transport. And it is very low computational cost to run 100 initial design optimization. Now this is the multi-objective optimization. This is the bread and butter of this project. We'll be using a response surface approximation in a software called Mode Frontier. We'll have 9 input variables and 2 objective functions, lift and drag. This response surface will be created using radial basis function. The response surface will be searched using a genetic algorithm to find an optimum Pareto design. This Pareto design will be validated both through CFD and through experimental results in the wind tunnel. And now the global component.
All right, so for the global component, well, there are a number of industries that have conducted research on multi-winglets, and aviation partners have actually already made winglets that are fence-tip as well as scimitar. And this has been implemented by Boeing and Bombardier, and the global impact is it's just the same as a regular aircraft would be, because these are just additions to the tip of an aircraft.
To conclude, when you have winglets implemented, you'll have consumption of less fuel, you'll have extended range for the aircraft, you'll also have reduced takeoff distance. Another benefit is less emissions, you have to increase your payload, become more efficient, overall increase your lift over drag ratio.
This is our timeline, our goal for this design project. And we'd like to acknowledge Dr. George Dilikovich, our mentor. our TA, Harry Kishar, for all his help, Professor Helmut Sobeski, and the entire Medrock Laboratory for their help so far.
All right.
Thank you.
Yeah, I have a few comments. First of all, the slides, the fonts of the slides, the ones that you have some pictures. Like, for example, bring up the one on the approach, the one that says approach, that one there. That's a very important graph you have off to the right there.
Yes.
Is there any way you could make that
Bigger?
well,
More
a little
background.
clearer? A little
Background.
clearer.
I could run it on a Unix system, yeah, I can.
Or instead of having a black background, could you make it a different background? That may highlight the data.
Okay, yeah.
You see what I'm saying?
Uh-huh.
Because that's a very important graph you got
Do
there.
you feel the need to explain the graph at all, or was that taken care of?
No, I don't think so. That
But-
explanation would be getting into the theory, which I
Exactly.
don't think.
The text is not visible, so you need to increase
Yeah, I
the
might
text.
just take it out and just say,
Yeah. Well, you need to make sure that the high points of that graph, the information you're trying to get out is somewhere on the slide.
yeah, somewhere in the bullet points. or
Right,
something.
exactly.
Good point.
The other thing is on the, and by the way, there are other slides with clarity issues as well, so have a good look at all of your
I have
slides.
that.
Some of the equations are not clear enough, so
Can you go to the CSV part?
yeah,
Those equations.
maybe you can make them a little bit bigger.
Okay.
Yeah. Now, on the analysis and the CFDs and all of that, the density altitude effects, to what extent was that included in the modeling?
Okay, so Fluent lets you specify the, we're modeling using density and kinematic viscosity. The airfoil, as you saw, the 2D PSU airfoil,
So temperature is also taken into account? Because
Fluent lets you
density
do that.
altitude is impacted
Yes.
by both
Exactly.
temperature and pressure.
Exactly.
Yes, it gives the option to input the
Yeah.
temperature.
So did you do that, or will you do that?
We will look into account. Obviously, if you do add the temperature aspect of it, you are increasing computational costs, so a trade-off has to be given off there.
Yeah, but it gotta be real.
Exactly, you do. So that'll be something to look into that.
Okay?
Yeah.
It's important to do that because we've got some smart people on the IAB. Even if I stay silent, they'll bring it up.
Yeah, temperature.
All right, so the other thing is on your timeline slide. Could you bring that up, please? Okay, I think you could do a little bit more work on the font size there on the left.
Okay.
I think the graphics and the months are clear enough, but font size,
Okay.
could maybe one or two more font sizes
We
greater.
should be able to do that.
Okay?
How come all your September is blank?
Yeah.
You didn't do
And
any
Ready
work?
for a project then? Just go ahead, just start. That's all.
A research phase?
Research.
That works too.
We can have it looking for a group.
Yeah.
You started in August, right?
Yeah,
Yes.
August and so
September.
September.
So did you not do any research, lit review, all that
We
stuff?
did, but no, we're looking for a project first, a good project that hadn't been done before, so.
Oh, I see, okay.
So
We went to
that's why we
training.
did multi-winglets.
We were engaging different advisors to see. what they
Okay,
had.
got it. Got it.
Shuffling.
April.
We hope to finish by March, actually, because there's a conference that's taking place in Barcelona in July. We want to submit the paper to.
So is it just the simulations or are you going to do a build any prototype?
Yes, at Embry-Riddle Aeronautical University, the wind tunnel testing, subsequent wind tunnel. I don't know if you're familiar, actually. Mr. UNESCO Rodriguez, 2010, senior design team, did an optimization of blended winglets. We're trying to prove ours are better. And so they already have the wing made. We have to add the winglet to it. And we'll compare the results.
Could you spell out scimitar as well? Because I'm not sure that everybody will be familiar with that, what that is.
SCIMITAR.
Yes,
We-
spell it out. What is it?
Okay, so, oh, you can say, okay, that's what you mean. Okay, so first of all, our project is now multi-winglet, not just the scimitar part. Scimitar is, it's a Japanese sword, okay? It's a very So imagine a sword like that, and the tip kind of curls back into one sharp point. Kind of like a shark's fin. That's basically a scimitar. And what it is, it's a retrofit. You have a blended winglet. Why design a whole new winglet? Just add the tip onto it, and if it makes it better, do that. So it's optimization of the tip cap.
Okay, yes,
So we may
spell
have
it
to
out.
attend that later. We
Yes.
just want to run the simulations on this.
No, I'm not questioning the
Oh, okay.
motivation or anything,
Yeah.
just the understanding of what
Yeah,
scimitar.
this is the actual name of our project now.
Yeah.
Constraint multi-winglets.
Did you include the cost analysis?
It is in our 25% report. We did not.
You need to include in this and
Do we need to talk about it because we cut it close by 2 seconds.
try to, I mean,
2 seconds.
You could have a slide on it and spend 30 seconds to talk about it.
or maybe 2, 3, just don't talk, this is the cost analysis and
Okay,
just
we'll definitely put that.
keep it.
Yeah.
Definitely put
And you need to include the time, human hours, and the distribution, work distribution. This is for all of them. No one has put the man hours
that. Okay,
and the estimated man hours. And in your case, it's more of computational, so you have computational costs too.
Yeah.
The software which you are buying is not a free one. So there is cost involved in that, so you need to include all those. Your cost
What will
analysis.
be the size of your prototype? Small one? I'm curious about you said you want to validate that in a week only.
Yes.
So what the cross section, I don't know, you already said that you don't have too much time, but maybe you can show how do you think you're gonna validate the prototype? So you close the loop with that. So you have some CFD simulations, you have some results, so you're going to compare with something that you expect to come up with, and then validate it.
That is
It's a huge,
great
by the
point.
way, it's a huge amount of work. Okay?
The wing that we currently have that's already made, which we'll just change the wingtip, it's about 20 inches. So we'll try to work around
Okay.
that, but if needs be, we may have to make a new wing.
And what velocities do you expect to validate?
Okay,
Are
so
subsonic, by the way, not.
we will be optimizing because the cruise aspect of the flight is so long. That's where most of the fuel is burnt. We will be optimizing winglets for the cruise part of it. Now, testing and validation, we will run a separate case study for the optimal design. Okay, at takeoff, because we know induced drag is
I don't think,
at takeoff, exactly. So we will be running a CFD analysis at takeoff.
very low
At
velocities.
exactly, at
Which
speed.
is the critical.
Exactly, perfect.
Condition.
We'll make sure the Reynolds number match and similar to this.
Exactly.
Okay, do you have a, yes, please.
Quick question.
Yes, sure.
For the multi-objective optimization that your software is using, you have like different sets of paired optimal solutions. How does it take one solution out of it, the one design that you want to use?
Can you please repeat the question back?
When you're using multi-objective optimization, there's no single solution.
No,
You will have a set of solutions.
exactly,
Out of them, you will have to choose one.
exactly.
Does your software, does it do it automatically or do you?
It will present us with a Pareto front, and based on our objective, which is maximization of lift, minimization of drag,
Okay, so
it will-
you have,
it will be a double objective optimization, correct? And we'll choose Pareto from the Pareto front, that's all.
and which method are you using for that?
Response surface approximation, we're using a hybrid algorithm to search the response surface. First of all, we'll test the response surface for 0 crossover, 0 mutation to make sure the response surface is accurate. And after that, we'll increase the generation, mutation, and crossover to obtain our virtual designs, our Pareto designs. Yeah, exactly.
Thank you.
Any other questions?
No.
Thank you.